Hello and welcome to ML with AP. The topic for today is ensemble learning. Let's learn. First thing first, what is this word? Is it ensemble or ensemble? It is derived from a French word and its correct pronunciation is ensemble. What it means in English is a group of musicians, actors, or dancers or performers who perform together. You must have heard this term ensemble in relation with movies or films. You must have heard something like ensemble cast of this movie, right? This is a great movie, one of my favorite. If you notice, there are so many great actors who are put together in one movie, and that's how this movie has become great. Okay, so that was ensemble cast in relation with movies, but what is ensemble learning? It's not that different. Like how many great actors, not just one actor, but many actors are needed to make a movie great. That was the concept behind ensemble casting. Similarly, in machine learning world, not one model is enough. You combine the knowledge or the predictive power of multiple models. You combine them, you join them together, and they will give you a much better prediction. That's the intuition behind ensemble learning. Okay, and how do you combine them? Either you average them in case of a regression setting, or you take the maximum vote or the majority vote in case of a classification setting. But ultimately the intuition is that by combining the knowledge of individual models, these individual models doesn't have good predictive power, but when they combine together, somehow magic happens and it gets a very good prediction, right? That's the intuition behind ensemble learning. Let's see. To give you an example, further example, I'm sure that you must have used Zomato or Yelp or any other food delivery app, or for that matter, Amazon, for ordering your groceries or any other thing, right? Now, whenever we buy on Amazon or we order food on Zomato or Yelp, what do? We see the restaurant rating, right? On a scale of 1 to 5, they will say, they'll show you little stars in yellow, and they will say it is 3.5, 4, 4.55. So suppose you have to buy a new air conditioner. You'll go on Amazon and you'll say all the sellers, all the products listed over there for air conditioning, and you will select based on the ratings. How that the rating comes? It's the verified buyers who have bought it in past have rated that product, right? So what we are inherently what we are getting out of this rating, we are getting that on an average, out of all the buyers who have bought, what is the average rating? That's what we are getting. So an individual buyer can rate it as 1 also, very poor, or can rate it as 5 also, very high, right? But when we see it on an average, then we see it as 4, 4.5, 3.5 and something, and we can make a mental model in our mind that, oh, okay, if it's 4 or above, then the product has to be decently good, right? It's good to buy. If the overall rating is below 3 or something, that product is not so great and we should stay away from that. This is also the Zomato, Yelp, or Amazon ratings, right? Or also in a way, what we call is ensemble learning, right? It is the learning of the group. It's the learning of multiple users or multiple buyers or customers who have put their knowledge together, and we are consuming the inference out of it, right? Let's move on. Now, there is something called wisdom of the crowd. It's a very old technique or philosophy. There is a very good experiment which National Geographic ran few years back, and I have a YouTube video of this. I'm not going to play this YouTube video. I will probably link it and you can watch it. It's a great video. I will try to tell you that what this experiment is all about, right? Okay, let me just show. So it was a National Geographic, and if you see, okay, here, let me just cut it out. Okay, so what this person is doing, there are a lot of balls or gum balls over here in a big jar, and this person is standing in a mall with a whiteboard behind him. What he's trying to do is that all the people in the mall over here, all the kids, the bunch of kids over here, right, in the mall, he will ask all of them that what they need to do is to guess. What do they have to guess? They have to guess the number of balls in this big jar. Okay? And what he will do, he will keep writing it on the whiteboard. So every individual person and their guess, he's writing it. So somebody is saying 2000, 1999, or 500 or 700, and he will keep writing down. Okay? What he's doing? This is called the wisdom of the crowd, or this is called the ensemble learning also. The intuition is exactly the same. The most interesting fact which came out of it, that none of the predictions were right. At the end of this experiment, none of the predictions were right. But if you average everything what was written on the board, or average every prediction which was made by individual, the people who were visiting the mall and who were asked this question, there were 20 or 30 people who volunteered, and the 30 numbers were written. If they took the mean or the average of those 30 number, it came very, very, very close to the actual number of the balls within that. Even though the individual predictions were way off, but their average or mean came very, very, very close to what the actual number of balls were there in the jar. What does it tell us? It tells us that individually we may not know something, but as a collective, or the collective wisdom of the crowd, they always know somehow that what is the right thing or what is the right answer for it. That is called wisdom of the crowd. How it is related to ensemble learning? We are doing the same thing. We are building multiple models. Each models have low predictive power. But when we combine everything together, the predictive power increases. When we average every person's which is written on the whiteboard, somehow the mean or the average was very close to the actual number, right? That is called the wisdom of the crowd, and that is the technique behind ensemble learning also. Now you will ask me that, hey, how it is possible that the mean is coming so close to it? So there is a rationale for that. The rationale is that over and above, there will be people who will underestimate it. So let's say the actual quantity of the ball was 2500. There will be people who will severely underestimate it. They will say 1000 or 500 or 400. Similarly, there will be people on the other side of that spectrum who will severely overestimate it. They will say 5000, 7000, 8000. On both sides of these, the true mean, there will be people, or the true number, there will be people who will be underestimating and overestimating. And for a large sample, if you ask from more than 20-30 people, what will happen is these underestimate and overestimate will cancel each other out. And what will remain is the true mean. The true mean will be very, very close to the actual number. And that's the intuition behind wisdom of the crowd, and that's the intuition behind your ensemble learning. Let's move. So that was ensemble method or ensemble learning. But does it work? Oh yeah, it does work. So I'm not sure if you have heard about the Kaggle and the Kaggle competition. It's a competition website. If you have not seen, take a look over there. It will have some competitions which are already running. I recommend you to participate in that as well. But before the advent of deep learning, and that started with 2012 when Jeffrey Hinton's group started using deep learning for all the AlexNet and ImageNet championship over there. There are many competitions which were always won by ensemble learning techniques, right? So ensemble learning technique was the king of all the competitions, because each individual model, no matter how good were there, were fairly and squarely beaten by ensemble learning. So one of the examples which I'm showing on the screen is the Netflix championship, and there was a $1 million cash prize, and it was won by the ensemble technique, and this was way back in 2009. Yeah, it was way back in 2005. But Still, it is a very good technique. It's a very good algorithm model to keep you under the belt, to use it in your data science journey, right? Okay. With that being said, let's move on. To understand ensemble learning, we got an intuition of the wisdom of the crowd. But there is another more technical reason also, and I will come to that. But for that to understand, you have to understand bias and variance trade-off. I have made a separate video about this bias and variance trade-off. If you have not watched, please go ahead and watch. It will be in, I have probably linked the description also, link in the description also. Apart from that, to understand this, probably you will need to understand decision tree also. So I have a playlist for decision tree also. If you have not watched, I sincerely request you to pause the video over here and go and watch the decision tree also. That will help you in understanding what is going to come. With that being said, let's understand what is, in 2 minutes, what is bias and variance. Let's see the downward picture first. These three graphs first. So it's a very simple regression problem. We have one feature which is called X, and we have one target variable which is Y. Okay, and what we have done, we have bunch of observation which are represented by dots in a scatter plot, right? So this particular middle figure, if you understand, this is what it is: one feature, one target or output represented in a scatter plot. What we are doing for this regression problem, and regression will be a continuous variable which you have to do the output, a numerical continuous variable, right? What we did is, suppose we grossly underestimate the true nature of the distribution. The true nature of the distribution is like a concave thing, right? Which looks visually, we can see that also. But we grossly underestimate that, let's say. And what we do is, we join we call it a straight line. Our regression line is a straight line, let's say. We call it as, we fit a straight line. Will it do a good job at prediction? No, it will not. Why it will not? Because it is not capturing the essence, the true nature of the distribution of the data itself. It is grossly underfitting it. This is a situation which is called high bias situation. High bias means we are building a model which is too simplistic to represent the actual nature of the data. Okay, that situation is called high bias. Whenever there will be high bias, that means we are underfitting. We are not mimicking the true distribution of the data with our model. Okay, this is called high bias underfitting situation. What is the extreme opposite of that? On the other side of that spectrum, the situation is high variance overfitting. Suppose it's the same scatter plot, and our model is a high degree polynomial, some weird polynomial of higher degree. And what it is doing, it is able to capture all the data points over here. It is almost like it is memorizing all the data points. In this particular case, do you think if the new observation comes and we have to predict the target variable for that, will this model will do a good job? No, it will not. This is the situation of high variance, overfitting situation. Why high variance? Because it is able to capture everything which is there in our training set. But when the test set comes, when a new observation comes, it will not be able to generalize well with that. Okay? Its predictive power will be very poor when the new observation will come. So both overfitting and underfitting are not good. Okay? Underfitting, that means high bias situation, not getting the true nature of the data distribution. Overfitting, high variance situation, chasing the noise also, but low predictive power, less generalization for the new observations. In middle of these two, the true nature of the data distribution line, which is represented by this. So it's neither a straight line, which is a high bias situation, neither a zigzag line of a higher degree polynomial, but this is a polynomial of order 2, somewhere in between. So this is a low bias, low variance situation. Here what will happen? the bias will be very, very low and the variance will be very, very high. Over here, it is high bias and low variance situation. Okay, but the good balance is somewhere in between. Not a straight line with an order of 1, not a high degree polynomial, but just a polynomial with degree 2 in this particular case. This is the meaning of high bias, high variance, low variance, high variance, low bias, low variance situation. What is underfitting and overfitting? I hope by this you understood. Let's jump on to the next one. Over here, this is nothing but representing this in a different form. So model complexity is our x-axis, error is our y-axis. What will happen in case of underfitting? Model complexity is very, very low. I'm fitting a straight line when the data distribution itself is concave nature, parabolic, quadratic nature. I'm fitting a straight line. What will be this? This will be a high bias situation, low model complexity. So this region will be my high bias situation. This region is high bias situation. Okay. So my error will be very high. And let's see over here. Yeah. Okay. Let's see this diagram maybe first. Okay. So my model complexity is there and prediction error is there. Over here in this region, both for my training and for my test, because I'm doing a gross underfitting. Okay. This is the reason of high bias, right? High bias and low variance. I'm grossly underfitting. My error for both training and test will be low. Correct? As I progress and I started fitting a better model, a 2-degree polynomial over here, what will happen? It will start fitting the data properly. So both for training data and for the new observation which will test data, my error will start coming down, and it will start coming. Suppose I started fitting degree 3, degree 4, and maybe this is 10th degree, let's assume. This is 10th degree polynomial. I started fitting 10th degree polynomial. What will happen? It will go in the range of high bias region. This is the high bias region. Why it will be high, and what will happen in the high bias region? Overfitting. What does it mean? That my training sample, the error related to training sample, this green line will keep going down. Why? Because my data is my model is changing the noise also. It is fitting the training data perfectly well. But a new observation come, it will throw a high error, right? So in case of new observation or a test sample, my error will start increasing, okay? But my training error will keep going down, keep going down as we increase the degree of polynomial or model complexity. Model complexity is nothing but you can assume it as a degree of polynomial which we are trying to fit. Over here with a straight line 1 degree of polynomial, quadratic somewhere over here, which is this thing. Over here 10th degree polynomial, right? So this graph, friends, I hope this graph is clear. So this region, this region is a high bias, low variance region. This region is a low bias, high variance region, right? The sweet spot is somewhere in between where we have to minimize our test sample and training sample. So the overall error has to be low. So this is the model which we should be selecting. Whatever complexity of the model is, this is the model which we should be selecting. So this is bias variance trade-off. This is again represented in similarly in a different form. If you notice, the model complexity is on the x-axis, error is on the y-axis. My bias will subsequently decrease. So if you move from left to right, my bias will decrease. My variance will increase if I move from left to right, right? So from low variance region to high variance region. And my error, this black line is the error. Error again will mimic the ball shape, right? However, my test error is there. It will be a ball shape error, right? So my error will come down for some time, and after that, it will start doing overfitting region, right? So below the dotted line, it is underfitting region. Above the dotted line on the right side, it is an overfitting region, right? High variance region. So this is also, so this is what bias and variance trade-off is there. Why is the trade-off? You can't have it both the ways, right? Either you get low bias, high variance, high bias, low variance, or somewhere in between there is a sweet spot where there is maybe relatively low bias and relatively low variance. But there is a trade-off which is always, you decrease one, the other will increase. You decrease the other, first one will increase. That's why the trade-off. Now, how does this fit in ensemble work? or how does this explain how ensemble works, right? So what ensemble will do is we can explain it through a bias variance trade-off, and this is the same figure which we are taking. By the way, this figure is taken from Elements of Statistical Learning. This is really considered as a Bible of machine learning. So if you have not, you grab an online copy, PDF or a book. I would recommend a book. This is really heavy stuff, but it's considered as the book for the machine learning. Okay, with that being said, let's go back. Now, if I have to, now one thing is sure that this is the sweet spot, right? Where my test error is relatively low and model complexity is somewhere in between. I'm landing in a situation which is low bias and low variance, right? Now, why this ensemble works in this particular case? I was saying that these models are, in ensemble learning, we are joining multiple models and we are combining them somehow, and we are getting the average out of it, or we are in the classification setting, we are getting the majority vote out of it, right? Let's say our models are very simplistic in nature. When we say very simplistic, that means the complexity will be low. It will be high bias situation, right? High bias. So my models either can be on this side, or it may happen that I have very complex models. So my models will lie on this side, on the right side of the graph, right? What is our aim? Our aim is to bring these models towards the bottom of the plateau or the bottom of the pit over here. And these models, which are complex in nature, again, I have to pull it down to the bottom, right? So for my complex model, right, high variance situation, I have to increase their bias. For the low variance situation, I have to make it more complicated or complex, and I have to increase their variance, right? This is what is happening in ensemble learning, right? Let's see. So how ensemble learning minimizes variance? So there are various types of or groups of algorithm in ensemble learning. The famous ones are bagging. One is which is bagging, which we'll just learn in a minute. But what bagging does? Bagging starts with very complex models, right? So it starts with the decision tree with real high depth of the trees, right? Again, if you have not seen the decision tree videos, please go ahead and watch that. So it starts with complex decision tree models, right, over here with high variance. And what we'll do is we have to minimize. The model is complex, we have to bring it down to minimize. How do we minimize? We are minimizing by taking the average out of it, right? So if the variance is very high and I'm taking the average, what I was doing over there also, in case of Zomato or Amazon, if you see, somebody has rated 1, somebody has rated 5, but on an average, when we take, we'll get a true picture, right? Okay, what is this product really worth? Is it a 4-star product or 3.5-star product? When we take the average, we are removing those noises, those outliers from here. Those one, a really bad customer, or somebody who is probably giving a fake review on Amazon on 5 ratings, right? Those all will go away, and will be stuck with the true majority. So in case of high variance, ensemble method that minimizes high variance. So in case of bagging, let's say we start from here and we go towards the downhill. In case of some other method like boosting, if you see, we start with very simplistic high bias methods, right? And we increase the variance out of it. And there is a way why we increase the variance. The way to increase the boosting variance is again through passing those models sequentially. And we are starting from a simpler model, and sequentially we are building a more complex model. That's the technique behind boosting, right? So what we are doing, we are starting with the high bias, low variance situation, and we are going this way. And some way in both the cases, in the bagging or boosting, in case of low bias and high bias situation, our goal is to go into the direction where we are meeting the downhill, the sweet spot. Okay, so this is why ensemble learning works, and the reason behind that can be explained best through bias variance trade-off. Now I was showing you over here that ensemble learning, there are various techniques of ensemble learning, right? So what I did was I asked ChatGPT, hey, list me all the ensemble-based algorithms in a tree structure. And it listed, I don't know, like 30 different algorithms. Apparently there are 30 different algorithms. We do not have time to learn about all those. So what we'll do is we'll restrict ourselves to the more popular ones or more successful ones. So this is what we are going to restrict it ourselves to. We'll learn about majority voting, which is really simple. We'll learn about bagging, boosting, random forest, which is again it's a bagging technique with a slight twist, and we are learning stacking also. Okay, so overall, if you see, there are three major classes of ensemble learning which is coming. One is bagging class. Random forest can be clubbed as a part of that. Boosting classes, there are several other methods in boosting. And stacking. We'll learn all these three. We'll try to get the intuition behind all these three. Okay? So although the ChatGPT has shown us probably 2030, we'll limit it ourselves to that. And since this video will become much longer, what I will do is, in this particular video, I'm going to limit myself to giving you the flavor or intuition behind ensemble methods, right? What ensemble learning is all about. You should have a feel or intuition about it. In next video, I'm going to deal with bagging, including random forest with maths and the code behind. And in the third video, we'll talk about boosting. Okay, so once we learn bagging with random forest, the third video will be about boosting, and different flavors of boosting we'll discuss over there with code examples. Okay, so this is how we will structure it. Now let's understand again. So I was saying that there are three major classifications, right? Bagging, boosting, and stacking. How does these work? So we start with weak learner. There is a concept of weak learner. So individual models are called weak learners. You remember the child in the video, in the YouTube video, which I was showing about the wisdom of the crowd? That is a weak learner. The child, if you have to ask to predict, he will never be able to predict the correct thing. He's a weak learner. But when we combine various weak learners, somehow their predictive power is increasing. And we have already known that why their predictive power increases. The answer lies in the bias variance trade-off, right? And there are several techniques for that. So the ultimate concept is that in ensemble learning, you combine several weak learners and you pass it through some pipeline, and what ultimately you get is a strong learner, right? Or a model which has a great predictive power. So as I was saying, there are three separate techniques under ensemble learning, primary techniques. One is called bagging, other is called boosting, the third is called stacking. All the models fall under one or the other. Under bagging, you will have random forest. Boosting will have gradient boosting, we have XG boost and other techniques. Stacking also has it, right? So in subsequent video, we'll be learning about bagging, boosting, and stacking. But let's get the intuition over here. So let's start with bagging. Bagging comes from, bagging is actually, we are joining two words over here, bootstrapping and aggregating. What is bootstrapping? Bootstrapping is nothing but, in bagging technique, what essentially we are doing, that let's say we have a big sample of 100 words, of 100 letters, right? This is our sample, this is our observation. What we do is, we take a subset of that 100, let's say 50 or 60 or something, okay? And we create multiple samples of size 60. Let's say we create 10 samples, okay? And we'll create this sample with replacement. What does it mean with replacement? We'll just see it in a minute. But ultimate aim of bagging is that from the same data set, from the same observation, we are taking samples and we are passing it to the models. When we are passing these individual samples to the models, the model is coming out with some output. In case of regression setting, it will come out with a continuous number. In case of classification, it will come out with a prediction, yes or no, if it is a binary classification. What we'll do is we'll average it out, or we'll do the max voting or the argmax of it. In case of classification, we'll count the maximum number of majority vote where it is coming, whether to yes or no, and we'll classify that. In case of regression, since it will be a continuous number, we'll say that, okay, let's take the average out of it. Boosting, on the other hand, what it does is it builds the trees. Again, over here also we have to build the tree. It builds the tree in a sequential manner. What it does is it will first let it pass through a model. Okay. After that, it will see that where all the model, my initial first model, has done wrong predictions. Okay, for which all observations it has done wrong predictions. Wherever it has done wrong prediction, in the next time when it is sampling in a sequential order, it will give higher weightage to that. What it is doing ultimately, by giving higher weightage, that the probability of getting selected for the next iteration is increasing. Correct? And when it is increasing, that means you are further zooming out on those sections of the data set which was not being correctly predicted. That's what you are doing. With boosting, this is the ultimate intuition, that you are zooming out on the data set in a sequential manner, that all those data sets which were not correctly getting classified. And ultimately, if you repeat this exercise multiple times, right, sequentially, in a sequence, your last model will have a great predictive power. What stacking does? Stacking is, again, over here, we'll pass our same sample to different models. We'll take the output of different model, but instead of like in bagging, we were doing the majority voting or averaging out, here we are not doing. We are passing all the outputs to a third model, to a newer model, to a what we call a meta model. We are passing output of all the individual models to a meta model, and the output of that meta model is being considered as is considered as the ultimate prediction. Okay, let's see it maybe with certain analogy also. Okay, and the analogy is interview. So interview setting. Let's say, what is the first thing we have to understand? And this whole video is about building the intuition. So let's understand this with this particular concept. What is decision tree? If I have to give you in an interview setting, then one person interviewing one candidate, suppose the manager is interviewing a candidate, okay, and there are 6 features or 6 traits on which that candidate is getting evaluated, like whether he's a team worker or not, whether he has done his all trainings or not, how good his skill is in Java or data science or Python or any other language, right? So these traits are there, or these features are there. One person evaluating one candidate on number of features is called decision tree. So if you recall my decision tree video, what we are doing, we are taking one sample, we have one sample observation, and we are splitting the trees based on one feature, and next again based on either the Gini index or entropy, we are splitting the trees right over there. So that is the intuition behind that, we can call decision tree. What is majority vote? Let's say we have now, instead of one person interviewing, we have 5 panel members, each with one vote, 5 models. So what will happen? Each will evaluate that candidate individually, and what they will do is they will do the majority vote. Let's say 3 in favor, 2 in not favor. This is how it works in parliament or in democracy also, like majority vote. Everybody has one vote, right? So all those 5 panel members, they will vote 3 in favor. If the majority says it is in favor of selecting the candidate, that interviewer gets selected. That is the concept behind majority vote. What is bagging? Bagging is slightly different. Now, we have got 5 panel members, but those 5 panel members are from the same business unit. That means they are running the same model, same algorithm. So if you are doing a decision tree, all 5 models have to be decision tree. That is the restriction with bagging. What we do is, we had this observation or the number of questions. Let's say we have 100 questions. We'll shuffle all these questions among these 5 panel members, and we'll ask that, hey, you randomly take 20 questions out of it and ask the student and judge based on that. Second panel member will also randomly take 20 questions. Now, question can be overlapping between panel member A and panel member B. That's fine. So it is sampling with replacement. This is the concept of sampling with replacement. That means that my individual samples need not be exclusive. They can overlap with each other. Okay. Again, what I will do, I'll build 5 panel members. Each have 20 questions from the bag they have taken. The bag consisting of 100, right? Let's say questions. Each have taken 20 questions. And they are going to evaluate the candidate on the same algorithm because they belong to the same business unit of the organization. And then what they will do? They will give their individual vote. So if it's a classification like select the candidate or reject the candidate, again the majority vote will kick in. That is called bagging. If it's suppose assigning a number to that candidate, their average will be taken. That will become a regression problem. It will still be bagging. What is random forest over here? Now in random forest, it's very slight tweak from bagging. In bagging, we are shuffling the observations. We are shuffling only the questions. In random forest, we are shuffling also the traits on which the candidate is being judged. Let's say on Python or data science or machine learning or Ruby on Rails or some other programming language, let's say. So those traits are also being shuffled among panel members, right? If that happens, it is called a random forest. What is boosting? Let's say now these panel members are not sitting one time and taking the interview parallelly. No, it is sequentially. So the first round of interview happens, and this is mostly happens in most of the companies. First round interview, some guy will come and interview you. What he will do? He will pass on the feedback that, hey, this person is good in this area but bad in these areas according to my observation. The second interviewer, right, or in the sequence who will come second round of interview, will take and will try to question the candidate only on those areas where he has done poorly, and he will try to judge that again. Third round, again he will do the same thing. This second round interviewer will pass on the feedback to the third round, and third round he will see that where he has done poorly. Over a period of time, what will happen is that ultimately when it comes to fifth or sixth round, he will be judged on all the parameters and everything will be scrutinized in a good way that nothing is left, right? So that concept is called boosting. What is stacking? Stacking is nothing but I was telling you that it's a meta learning, right? So we have individual models and we have a meta model. Suppose multiple interviewers have interviewed, but they are not deciding among themselves like how we are doing the bagging or random forest. What they are doing is they are passing all their input. Yes, yes from my side, no from my side, no from my side, yes from my side. All 5 panel members are sending it to, let's say, director of that business unit, who is the final authority for selecting or rejecting a candidate. They will pass all their inputs, 1 0 1 0, yes no, yes no. Ultimately the director will see that how many yeses have come, how many no's, and based on his model or his thinking, he will take a call, and that will become the final call for selection or rejection. That technique is called stacking. So I hope, friends, with this intuition of interview questions, you got the idea that what is decision tree, what is majority vote, what is bagging, what is random forest, what is boosting, what is stacking. Okay, I hope you got that. Let's see the build our further intuition, especially on bagging, boosting and stacking techniques. So in bagging technique, what is happening? We have a training data set. What we took, we did a sample with replacement. Sample with replacement means, let's say there is 1 to 100 observations on there, and every subset will get 20 observations. Every subset, these red squares will get 20 observations. This has got 20 observations. This also has got 20. This, everything has got 20. And similarly, let's say we have 10 such subsets which we have created. Now sampling with replacement says that there will be an overlap of observation between subset 1 and subset 2 or any subset, because we are not mutually exclusive type of sampling we are doing. We are doing sampling with replacement. That means the pool will remain intact 100, and the same probability I am picking again the new thing. So even in subset 1 itself, there can be one observation which can appear more than one time, 2 times, 3 times, 4 times it can appear. Same observation can appear in subset 2 or subset 3 or subset M also, right? So that is the concept behind bootstrapping. And the word bagging came from bootstrap aggregation, the first word and this. So bagging, bootstrap aggregation. Okay. What we'll do after that, once we have these samples with replacement, we'll pass it to the individual models. Now these models are weak learners, right? Remember the boy in the video, these are weak learners. Once we pass it to them, everybody, let's say it's a classification, everybody will give a prediction. Yes, no, yes, no, yes, no, yes, no. What we'll do aggregation over here. Aggregation in case of a classification, what it will be? Majority voting. Maximum number of yes or no, that class will be assigned. In case of regression setting, what will happen? Take the average, take the mean and give the prediction. This is the example of bagging. What is boosting? Boosting, I was telling you, the interview, remember the interview? It is sequentially done. One interviewer sending it to the feedback to second interviewer sending the feedback to third. Similarly, we did a subset over here. We passed it through weak learner. He did the testing. All the false predictions, whatever has come, wherever that candidate has not been able to answer questions, these things will be zoomed on now in the second round. In the second round, there will be higher probability of picking those observations where we have made the false prediction, and it will be passed again to a weak learner. This weak learner is nothing but an interviewer, and he will again, but this time my subset consists of greater chances that will have those observations over here which has false prediction last time. What will my model do? My model is zooming on those observations only, right? It is giving more emphasis to those observations, and hence those are improving. So overall predictions after multiple iteration of this, overall prediction will be higher. So that is the concept of boosting. Third is stacking. What is the concept of stacking? I told you about the meta model. The director of the business unit will come and take the final call. We have a training set, observations. We are passing it through multiple models. Each model is giving a observation, right? So model 1 will give observation, model 2, model 3. These observations, I'm not doing an aggregate of this. I'm not doing an argmax. I'm not counting a majority vote. No, I'm not doing anything. These outputs of these become a new data set for me, a new training data set for me. And where it will go, I'll feed all these outputs into another model over here. And the output of that model will be my final prediction. Let's take it with an example. Let's say we have to do a binary classification problem, okay? Yes, no type problem, right? 1-0 type problem. Classification, simple. We have bunch of training data sets over here, okay? We are passing it through the first, these red squares are our decision tree models, let's say. These are our decision tree models. We passed it through decision tree. All our decision tree, we passed it through them. Every model will predict yes. If suppose the new prediction will come, everyone will predict yes, no for each of the observations. It will say all these yes, no will form my new training set. Over here, this meta model could be another model. It could be decision tree also. It could be, let's say, logistic regression. This meta model, let's say, is a logistic regression. All these inputs went into the logistic regression model. What will be the output of logistic regression? Yes, no. So instead of taking the argmax or the mean or at this stage, in stacking what we are doing, we are passing it through a meta model and taking the output of the meta model as final prediction. This meta model in our analogy, in the interview analogy was what? It was the director. So all the interviewers are giving the interview, but all the inputs are being taken to this meta model to the director, and he is finally giving the say that whether the person is rejected or selected. So friends, I hope I will close this video over here. I hope you got the solid foundational understanding and intuition behind ensemble learning, and what is bagging, what is boosting, what is stacking, right? In next video, when we meet you, I'll discuss about bagging with random forest, and we'll discuss some code also over there. And the third video will be discussing about boosting. With that being said, let me close this video over here. Bye.